This is William Tomos Edwards from Bright Studies, and today I am going to show you the easiest way to solve for the equation for an oblique asymptote. Now, when we're dividing one polynomial by another polynomial, just like this example we have right here, sometimes you might have a situation where the highest term in the denominator is being raised to a power just one greater than the term that is to say, the term in the numerator being raised to the highest power. Well, it's being raised to a power one greater than the term in the denominator raised to the highest power in the denominator. Such the other situation where what's dictating the fact that you've got a oblique asymptote is this fact you have these two terms, the highest in the numerator and denominator respectively, and one is n, the other is n minus 1, right? A sub 1 times x to the fourth power divided by a sub 2 x to the third power, and so on and so forth. And that creates an oblique asymptote. The oblique asymptote means that as the ratio of those two polynomials is seen above, as that approaches infinity, as x approaches infinity, then the curve, the graph of that curve is going to start to approximate this linear equation. It's going to start to approximate a sub 1 divided by a sub 2 times x plus b. Okay, well, that's easy solving for the slope of that linear equation. Pretty easy. A sub 1 divided by a sub 2, right? The coefficient on the x raised to the highest power in the numerator divided by the coefficient on x raised to the highest power in the denominator, right? Multiply that by x, that's a slope. But what about b? How do we get b? So usually when you're in this situation, you guys know you're on an exam, you have to do this, you have to do polynomial long division, you have to do synthetic long division. That is how you solve for b, the intercept. But I'm going to show you today there's a way easier way to do it, and so we'll get started on that. So we're going to start with this theorem. You take the polynomial, right? You take the rational function, the ratio of the two polynomials, whatever it is, okay? You take that and you subtract the linear equation, a sub 1 over a sub 2 times x, right? That equals b. The limit, that is, as x approaches infinity. The limit as x approaches infinity of the rational function, the ratio of the two polynomials, minus the linear equation, that equals b. That equals the intercept. Okay, so how is that? Well, this proof might not be as rigorous as can be. I don't think you guys care about that, but I would say the proof is pretty simple. Ultimately, what we're going to do is we're going to say, yeah, by definition, as the limit as x approaches infinity of the difference between the linear equation, right, for the oblique asymptote and the curve, the graph of the original function, the ratio of those two polynomials, right, as x approaches infinity, the difference between those two gets to 0. The difference between those two approaches 0 because the idea is that the ratio of those two polynomials is just simply going to approximate the linear equation as x approaches infinity, right? So the difference between 0. Therefore, we know the limit as x approaches infinity of the difference between them equals b. Perfect. So then where do we go from here? Okay, well, there's a corollary. The corollary is what's going to make it way easier for you guys to solve for b, to solve for the equation of the oblique asymptote on an exam. Okay, this is the good part where we actually see how it's going to be 10 times easier now, or at least twice as easy compared to doing the polynomial long division. So let's look at the corollary. Okay, so the limit as x approaches infinity of the ratio of those two polynomials minus that equals b. Okay, so we start to simplify things, right? We find a way to combine those fractions, right? So we're going to multiply a sub 1 divided by a sub 2 times x, right? We're going to multiply that by the denominator, right, of the original function. That's what we're going to do. We're going to multiply it by the denominator, right? It's showing up in all those places, right? So we can have a common denominator and do that. Okay, great. So let's continue to simplify things then. So we continue to simplify. Okay, we end up with this beautiful situation where what we're going to find actually is that this one and this one cancel, right? Perfect. So finally, it simplifies to this. Okay, I don't want to give it away just yet, but finally, what it's going to simplify to is this right here. So here's the beauty of it. All the other terms in the polynomial, whatever power they're being raised to, it doesn't really matter. Okay, it doesn't really matter because there's only three terms that matter. The beauty of it is there's only three terms in either the numerator or denominator that can dictate the behavior of this limit as x approaches infinity. Therefore, this leaves a very narrow range of options for what the intercept b can be. Oh, I almost forgot. Just for some rigor, we're just going to add equals b. Okay, equals b. So this is what I'm getting at. So this term right here, I'll circle in red, that can potentially dictate what happens to the polynomial as x approaches infinity. This one in the denominator, that one raised to the highest power in the denominator, that can certainly dictate the behavior of the polynomial as x approaches infinity. And finally, this one right here, that one can dictate the behavior of the polynomial as x approaches infinity, but indirectly, because the reality is that this term up here, I'm going to put in more of like a different shade of green. That term right there is just coming from that term, okay? It's being created by that term in the denominator pretty much, right after we simplify everything. So what we're really going to end up with, though, is a situation where to really simplify things, there's only a few coefficients. That's the real key thing here. There's only a few coefficients we're going to worry about. Okay, B1, that's the coefficient on the term raised to the second highest power in the numerator. Okay, A2, A sub 2, that's the coefficient on the term raised to the highest power in the denominator. And then finally, we're going to worry about this term, b sub 2. That's the coefficient on the term raised to the second highest power in the denominator. So that's all that we're going to look at. Okay. So let's see what this means. Well, what this means is, okay, you only have four options for what the for what b can equal. Okay, what we're going to end up with here in the end is b can only equal one of these four options. So let's say, for instance, that I'm going to use a different color. Let's say that the k sub 1 is equal to n minus 1, right? Let's say the k sub 1, the k sub 1 there is equal to n minus 1. Well, then you know that term in the numerator, right? So the power of k sub 1 is being raised to the same power, right? The same n minus 1 in the denominator. Therefore, as x approaches infinity, they're just going to cancel each other out. You're going to get b sub 1 over a sub 2, right? And that's exactly what you get in this first option. Keep in mind that first option is contingent upon the k sub 2. Okay, the k sub 2, I'm just going to circle that one, right? K sub 2 right there. and I'll circle the K sub 2 right there. Okay, so what that one is contingent on is or sorry, what that first answer is contingent on is the K sub 2 is less than n minus 2. Because if it's less than n minus 2, then that means you add 1, right? You do the plus 1. Well, that's going to be less than n minus 1, okay? And therefore, it cannot dictate the behavior of this thing as x approaches infinity. So if you have the situation where the K sub 1 equals n minus 1, and the K sub 2 is less than n minus 2, then what this means is that what this means is that only the b sub 1 over a sub 2 becomes relevant to the limit as x approaches infinity, right? That is if the k2 is less than n minus 2. That means it can't dictate the behavior of the function. So then we get to the next one, okay? Then next, we're going to get to this yellow one. And so for this yellow one here that comes next, what we can see here is this is what you're going to get if the k2 equals n minus 2. Because if k sub 2 equals n minus 2, then k sub 2 plus 1 equals n minus 1. Well, therefore, it can dictate the behavior of the function as x approaches infinity. And let's say, like in this example here, that k sub 1 is less than n minus 1. Well, then what that means is you're going to get that term divided by a sub 2 as x approaches infinity. So you're going to get a sub 1 times b sub 2 over a sub 2 squared minus all that minus. And I know that's obviously a more complicated one, but just memorizing that is way easier than doing polynomial long division or synthetic long division, I think. Especially you can commit that to muscle memory. It is just simply, you know, that formula with 3 separate numbers in it. So, okay, but then let's say that k sub 2 does equal n minus 2, right? Let's look at this next one here. Let's say in that case, k sub 2 does equal n minus 2 and k sub 1 does equal n minus 1. Okay, well then they can both dictate the behavior of the function as x approaches infinity. And in that case, that's what you're going to get. So in that case, if that's the case, that those are the powers they're being raised to, right? The k sub 1 is really n minus 1. The k sub 2 is n minus 2. Well, then you're just going to get the combination of those ones, right? Then you're just going to get a combination. I want to kind of emphasize what we're doing, right? We're taking the green one, right? And we're taking that the gold one, right? And we're subtracting them. We're combining them rather. That's technically like a sum of those two, right? We're just combining them together. So there you have it. It's you know, something that can be committed to muscle memory, and just practice a lot of those that way, and you'll see it. Now the other option, let's say that k sub 2 is less than n minus 2 and k sub 1 is less than n minus 1. Well, then the numerator is relatively just going to get smaller and smaller and smaller as x approaches infinity. The denominator is going to get bigger and bigger and bigger, and then basically it's just going to approach 0. It's just b equals 0. So that's the other option, b equals 0. Anyways, best of luck using this technique on the exam. Try and commit it to muscle memory, and it will help you out to solve for these oblique asymptotes. This is William Tomos Edwards from Bright Studies.